Hello, everyone. I'm sure that you are excited to begin your journey of class 9. And you must have also gone through the Ncert textbook, which has been recently released. Our first chapter is number systems, the base of which you must have done in class 8. So I'm going to give the introduction to the number system, and then we'll gradually solve the questions related to it. So in the number system, the first thing that we have to understand is the number line. Now, in the number line, you see 0 is at the center, and this is a line that is extended to the right as well as to the left. So when I talk about line, it is of indefinite length. It is extending to the right as well as left. So we are putting these arrows. So number line has infinite length. On the right side, you have positive numbers, and on the left side, you have negative numbers. So that's how number line is represented, right? So moving forward, when you go towards the right, you find positive numbers. So here you have 0, 1, 2, 3 up to infinity. And then when you go to the left, you are getting negative numbers. So this is the number line. And if I talk about the numbers on the right side, 0, 1, 2, 3, 4, 5, 6, right of 0, when I start with number 1, 2, 3, and goes up to infinity, then these type of numbers are called natural numbers. So 1, 2, 3, these numbers 1, 2, 3, and so on up to infinity are called natural numbers, and natural numbers are represented by n. Natural numbers are represented by capital N. And if I am starting with the 0, here I am starting with 1, here I am going to start with 0, and I'm going to 1, 2, 3, 4, all these numbers right up to infinity, then these numbers are called whole numbers represented by W, right? So natural numbers are starting from 1 and goes up to infinity, and this collection of numbers is represented by n called natural numbers. And if you are starting from 0 and going right up to infinity, 0, 1, 2, 3, 4 up to infinity, these are called whole numbers, and these are represented by, this is represented by the alphabet W, right? Moving on further to the type of the number system that you are supposed to do, we are going to go to the next part, that is integers. So if I'm looking at integers, natural numbers was represented by W, n, and whole numbers are represented by W. Here, integers are not represented by I. Okay, the natural tendency for us is to denote integers with I, but it is not the case. Integers are represented by the symbol Z. Now, why is Z? Because Z is coming from the German word zahlen, which means to count. So natural numbers is n, whole numbers is W, and integers is Z, because Z is coming from a German word. It's not English, it's a German word zahlen, which means to count. Okay, so far we have done what are natural numbers, what are whole numbers, and what are integers. Moving further to the next part of the chapter, we find that the next thing discussed here is rational numbers. Now, when we talk about rational numbers, in class 8, you did this definition that rational numbers are numbers which can be expressed in the form of P by Q, where Q is not equal to 0. The denominator should not be 0, because whenever we are dividing a number by 0, that is not defined, or it is infinity. Infinity is such a large number that we cannot define it, we cannot calculate it. So that is why we say it is not defined. So rational numbers are anything in the form of P by Q. So a natural number is a rational number, right? We have any natural number, it can be written as 5 by 1. You can have any fraction, all fractions are rational numbers. So anything in the form of P by Q. So what is this P by Q? It's a fraction. So it is a fraction, and therefore the collection of rational numbers is denoted by Q. where Q stands for the word quotient, right? When you divide something by something, 7 by 2, then what is happening? When you divide, you get a quotient. Now, because of that, the collection of rational numbers is represented by Q, right? Because Q stands for quotient. And R is called a rational number. As I said, it is represent the free form of P by Q, where P and Q are integers. Just now we understood what are integers. And if P and Q are integers, that is numerator, P is any integer, -1, let's say, and Q is 3, it should not be 0. That's it. Denominator should not be 0. Why are we insisting that Q should not be 0? I just now explained, because any number by 0 is not defined. So this is the meaning of a rational number. A rational number is a number in the form of P by Q, where Q is not equal to 0. Please remember, a collection of rational numbers is represented by capital Q, because Q comes from the word quotient, and rational number is represented by P by Q. A number R is called a rational number because it is written in the form of P by Q. Remember that P and Q should be integers, and Q should not be equal to 0. This is very important. Moving further in the chapter, we have some questions here. The first question, are the following statements true or false? Give reason. Every whole number is a natural number. So just now we did natural numbers are starting from 1 and goes up to infinity. Whole numbers are starting from 0 and goes up to infinity. And the third, every rational numbers were numbers in the form of P by Q, where Q is not equal to 0. So now let me go to the first part. Every whole number is a natural number. So every whole number, if I look at 1, 2, 3 up to infinity, all these whole numbers are natural numbers. But if you look at this number 0, it is a whole number, but it is not a natural number. So this statement is false. Every whole number is a natural number is false, because 0 is a whole number, but it is not a natural number. Second part, every integer is a rational number. So every integers could be negative, integers can be positive, integers can be also be 0 itself. So you can have any number from negative infinity to positive infinity and also 0. All these numbers are rational numbers, because I can write all these numbers as denominator 1. So -3 I can write as -3 by 1. 2 I can write as 2 by 1. Even 0 I can write as 0 by 1, because 0 by anything is 0. So every integer is a rational number is true, because it can be expressed in the form of m upon 1. And the only criteria, we said that it cannot be rational number if it is P by Q, where denominator is 0. So it should not be equal to 0. And whenever we are writing an integer, we can write it as 1. And therefore, that is a true statement. Next one, every rational number is integer. Every rational number is integer is false. There may be some rational numbers which are integers, but not all. So if I'm looking at a number like 1 by 7, this is a rational number because it's in the form of P by Q, but it is certainly not an integer. If I look at -3, this is a rational number because it's -3 by 1, and it's also an integer. So it works for this, but doesn't work. Here they have used every rational number is an integer. So that is going to be false, because we have lots and lots of fractions which are rational numbers. In fact, all fractions are rational numbers, but certainly they are not integers. So that's our example 1 explained. Now, example 2, how to find out numbers between two rational numbers. So here they've asked us to find out numbers between 1 and 2. So there are infinite numbers lying between them. So what are rational numbers? Rational numbers could be any number which are terminating numbers, or it can be a fraction which will give you a non-terminating but repeating decimal expansion. So I'm just going to explain this to you. So suppose I'm going to divide 5 by 2. This is a rational number. I'm going to get 2.5, right? So these type of numbers are called terminating numbers. So all terminating numbers are rational. I can also give examples like 1 by 3. When I try to divide 1 by 3, I get 0.3333. It will go on recurring. That is called 0.3 bar. So these are called non-terminating numbers, but recurring or repeating numbers. So both these categories, either the number is terminating or the number is non-terminating, repeating, both these can be classified as rational. Okay, so what are rational numbers? Rational numbers can either be terminating numbers or it can be non-terminating but repeating numbers. If they are non-terminating, remember they have to repeat or they have to be recurring. Repeating means the number will go on, it will never end. It will keep on repeating. Now here the question is, find 5 numbers, rational numbers between 1 and 2. So you can give 1.1, you can give 1.2, 1.3, 1.4, 1.5, 1.6, all these. Why? Because they are terminating numbers. All terminating numbers are rational. Okay, so you can give lots and lots of examples. 1.58, anything less than 2 but more than 1 in decimal expansion can be given. So these you have to write any 5. So you could write this any 5 numbers as per your choice. Then we go to the next part, that is, the question says, is 0, this is the first exercise, is 0 a rational number? Is 0 a rational number? So if I look at 0, 0 can be written as 0 by 1 or 0 by 2 or 0 by 3. It doesn't matter because all this is going to give us 0 itself. And it is in the form of P by Q. And the denominator should not be 0. That's the criteria, right? So here the denominators are not 0. Denominators can be anything, 1, 2, 3, 4, but the value is not anything. So 0 by 1 is 0, 0 by 2 is 0, 0 by 3, 0 by 100, 0 by 1000. Whatever you are putting in the denominator is going to come. So 0 is a rational number. Answer is yes, because it can be expressed in the form of P by Q, where Q is not equal to 0. That's the answer, right? So 0 is a rational number. Why? Because 0 divided by any number is going to give us 0. And it can be expressed in the form of P by Q, but Q should not be equal to 0. Find 6 rational numbers between 3 and 4. You have to find, just now I told you, any 6 can be written 3.1, 3.2, 3.3, 3.4, 3.5, 3.6, whatever you can write here between 3 and 4. All these numbers are rational numbers because they are terminating numbers. Find 5 rational numbers between 3 by 5 and 4 by 5. Now we are dealing with fractions. Now, the one good thing about this question is that it is having the same denominator. Now, in the exam, suppose you are given a question like this, then the denominator is not same, then you will have to take the LCM of this. So, LCM of 2 and 3 will be 6. 2 goes 3 times, so this is going to be 3 into 3, 9 upon 6. Here, LCM is 6. 3 goes 2 times 2 into 2 is 4. So, 4 by 6 and 9 by 6. The first thing is that the denominator has to be same. So here, fortunately, the number of steps will be less because you have already denominator same. Here I had to make it same. So this is not given in the book, but I'm explaining. If denominator is different, then what happens? You have to make the denominator same by taking the LCM, right? So what are the numbers between 4 by 6 and 9 by 6? I can write 5 by 6, 6 by 6, that is 1 itself. You can have 7 by 6 and 8 by 6 and so on. Right? Now here, 3 by 5 and 4 by 5. Now I'm looking at 3 by 5 and 4 by 5. So already, as I said, the denominator is same. So between 3 and 4, there is no whole number or natural number. So what we can simply do, we want to find out 6 numbers. So what I can do is multiply and divide the numerator and denominator by 10. Right? So just multiply and divide by 10. So what am I going to do? 3 by 5, multiply and divide by 10. 4 by 5, multiply and divide by 10. I'm going to get 30 by 50 and I'm going to get 40 by 50. So what am I doing? I'm converting this 3 by 5 and 4 by 5 to an equivalent fraction. 3 by 5, I've got 30 by 50 and 4 by 5, I've got 40 by 50. Now, how many numbers are there between this 31 by 50, 32 by 50, 33 by 50, and so on? You can write any number, any 6 numbers up to 39 by 50. All this will be marked correct. So 5 rational numbers between 3 by 5 and 4 by 5. We have found out. First, we need to take the LCM. After taking out the LCM, multiply and divide by 10. You can multiply and divide by any number, but there should be 6 numbers. So you could have multiplied and divided by 8. You could have multiplied and divided by 15 or 20. But I did with 10 because that is the easiest. Multiplying and dividing by 10 is easy. Just add zeros. Then we go to question number 4. Every natural number is a whole number. Every natural number is a whole number. So I'm talking about natural numbers. We already revised that natural numbers are starting from 1 to infinity. All these are whole numbers. That is true because 1 is a natural number. It's also a whole number. 2 is a whole number. 3 is a whole number. So whatever numbers you're taking from this series, everything will be whole numbers. All natural numbers are whole numbers will be a true statement because natural numbers start from 1 and end to infinity, and all the numbers in this collection also belongs to the collection of whole numbers. Every integer is a whole number. Now here, whole numbers are starting from 0. And integers will also have negative numbers. So minus 3 is an integer, minus 2 is an integer, but it is not a whole number. So there are some integers like 5, 6, 7. These are integers and they are also whole numbers. But when I talk about negative numbers, they are integers, but they are not whole numbers. So this statement is going to be false. Every integer is a whole number is going to be false. Why is every integer a whole number false? Again, I'm explaining because negative numbers like minus 2, minus 3, minus 4 can be integers. They are integers, but they cannot be whole numbers because whole number starts only from 0. There is no negative number in this series. Every rational number is a whole number. So this is also going to be a false statement because we said that rational numbers are what? Numbers in the form of p by q. Numbers which are in the form of a fraction. So I have a fraction 3 by 5. So this is a rational number. This is a rational number. But if you analyze this, this is not a whole number. 3 by 5, 1 by 2, 7 by 5. There are so many fractions which are rational numbers. All fractions are rational numbers, but they are not whole numbers. So every rational number is a whole number is false. So this is the first exercise and introduction to the chapter. In the next video, I will be explaining exercise 1.2.